Hello and welcome to a new lecture in a series on machine learning. In the previous video, we gave some basic math needed to start talking about some concepts in machine learning. And today, we're going to be talking about the first topic in machine learning, which is regression. Particularly, we'll be talking about one of the most famous and common types of regressions, which is linear regression. We're gonna be seeing later other types of regressions, but this is a nice start with the basic level in the field. So what is regression in general? Well, like generally speaking, if I want to say it roughly, like when we do regression, we are actually trying to estimate some relationship between a dependent variable and one or more independent variables. For example, let's say you're interested in predicting the prices of the houses in a certain region in a certain year. So, or this year. So what you do is that you use some data you collected from previous years and you use some features that that were important in determining the price of the house. For example, the size of the house is certainly one important factor in determining the price of the house, right? So we collected data, say from last year, we collected data of sizes and prices, and then we try to estimate the pattern that's happening in this data, and we try to apply this to this year, for example, to predict something. Or it doesn't have to be for different times. It really can be like, let's say the price of a house, for example, when the size is X, you know that the price is Y, and when the when the size is X2, you know the price is Y2, and so on. So you know the price for like a number of sizes, but you don't know it for any size, and you want to predict the price for, I don't know, for a particular size of interest. Then you'd need to predict the overall pattern, and then use that predictor to estimate the price of the house with the size of interest. So this is, as an overall idea, this is what it is about. Um, however, linear regression can be a little bit more complicated than that. For example, we can take a third example I was thinking of. I mean, say we want to predict the final grade of someone, final grade of a student from their, I don't know, midterm grades. So let's say you have a data for 10 students, and for each student there are 3 midterms, and you know the grades of these midterms, and you know the final grade of that student. But what you don't know is how that final grade is calculated, right? So there's some way, like there's some percentage distribution for these 3 midterm exams, but you don't know what that is. So what you do is you collect some data. You collect this 3 grades, 3 midterm grades, and the final grade for a number of students, and then you try to predict the pattern. So as you see here, the dependence here was on one variable. For example, here it was only on the size. However, here, like, we have more than one variable. So we'll see after we discuss the one variable case that, in fact, we can handle more than one variable in which case it's sometimes called multiple linear regression. So we'll see how this goes. Okay, so I want to start by noting an important thing that is important to know for general like generally when working in machine learning, right? So it's very important to visualize the data. Like when you plot the data, for example, let's say the data usually denoted by D, and it's like it's a set of tuples of this form, and for each tuple xy you plot it as a point in the plane, and then you observe what happens. You observe what kind of pattern is happening, because if we plotted this data and you come and say, well, this is a good predictor, well, that claim is false. It's not really a good predictor. Even if you come and say that, I don't know, this is a good predictor, well, that's also not true. So there is some like curvature that we can't capture by the linearity here, right? So we'll see that this is, for example, such data can be like to predict the pattern happening in such a data set. We need, for example, polynomial regression. We'll come to this. But I wanted to note that plotting the data is very important to capture the relationship, to try to predict the pattern. And more than that, why is plotting the data important? Well, plotting the data important because sometimes in the data set, the data set, like we can't say it's 100% reliable. Sometimes we might have false, like we might have like some noise in the data. We might have some data that is not accurate, right? So we might have a tuple x and y where y is not actually a good like label, as we will gonna call it in a few. Y is not a good label for x. For example, one particular thing that can happen is what's so-called an outliner. So you might have a data point that is off the pattern, right? Like you have a pattern that's happening, and then there's this one or a few data points that are like off the pattern. So we call this an outliner, and we usually ignore this. We usually try to not let this affect the overall pattern happening in the data. So we're gonna discuss these things in details, but I'm trying to give an overview before we get into the math actually. So let's talk about some fundamentals. So what is the linear model, or what's the linear regression model? So from the name, linear means I'm gonna use a linear relationship between x and y. I wanna predict y by looking at a linear combination of x and the constant 1, for example. So if we want to predict y by a line of the form beta naught plus beta 1 x, the only thing that would be missing in this case is beta naught and beta 1, right? So if I tell you I want to predict y by a line, like by the line beta naught plus beta 1 x, I need to know beta naught and beta 1, but we don't know that. And we know every different like choice of beta naught and beta 1 gives a different line. And hence we need a way of picking these beta naught and beta 1. That's not like a random choice. There should be a way of picking these. And the way we're gonna pick these is by taking so many samples, just as we mentioned above, like collecting a data set so that we can predict the pattern happening in the data. Let me just introduce some terminology here. So the y here that we're trying to predict is usually called a response, but more generally, like a more famous term, it's called a label, or the target variable. So this is what it's usually called. Let me also not use predictor here for X. So X is usually called the feature. So the feature X is used to predict the label Y or the target Y. And as you know, beta naught is the intercept and beta 1 is the slope of the line. Okay, so why are we starting with this type of regression? It's because it's just a simple thing to start with. But like it's not necessarily the best thing to use because it depends on the type of data that we have. We may have a data that looks like this, for example, in which case using a line might be good. But I mean, we may have something like this. We may have some data, I don't know, something like this. Like that. In which case using a line won't be the best ideal thing to do because, I mean, if you choose such a line, that's not going to be a good choice. In which case, like, some other types of regressions might be needed to do something like this, say, for example. So we're going to come to this later, but linear regression can be useful sometimes if we know a priori that the data has some sort of linearity property that we can exploit. Okay, so as I mentioned, the unknown here is, so this would be the line y equals to beta naught plus beta 1 x. So as I mentioned, the unknown here, like the unknowns are beta naught and beta 1. These are the things that we don't know. Once we know them, we actually know the predictor. So once we know what beta naught and beta 1 are, we can plot that line and we know the predictor. Meaning, if I give you now any x, you're gonna predict the y by this. It's gonna be the prediction of you. If we give you some x naught, you're gonna predict this by y naught. I wanna note something here. Notice that, for example, let's say this was the size and this is the price of a house, right? So we only started with a finite number of observations, right? So we only knew a priori that, for example, for this size, this is the price, and so on and so on. So we only knew this size-price relationship for finitely many variables, and now I'm able to choose any size that I wish and predict the price for that. So so the next thing we're gonna try to do is determine how we can find the beta naught and the beta 1. Okay. So we're gonna introduce something called a residual. But before I do that, I guess let me just introduce one more terminology. We're gonna denote by D and XI, from I equals 1 to N. We're gonna denote by this, we're gonna use this to denote the data set that we're working with. So we have some data set and we're trying to predict the general pattern. As I mentioned, we only have a finite number of observations. So one thing I want to note here is the following. How can we predict the beta naught, or how can we find the beta naught and the beta 1? Well, if you see here, if I plot this data, let's say I plotted this, and this is x1, this is x2. Maybe it's not the best way to do it here. So let's say this is x1. Over here, this is x2. So I know this for let's say this is x, I don't know, 9. This is x20. So I plotted this data, and now I'm trying to predict the pattern. So one naive way of doing this, or one way that you might think is a good way of doing it, and you're right if you're thinking like this, is how about that we minimize the distance between the line and each data point? Like if I minimize the distance between the line and each data point, I'll be um, I'll be getting a good line, right? Because I mean this line is bad because it has bad distance, let me call it, between the data points and it, right? So we want to minimize the distance between the line and each and every data point. So, like, how can we do that? Well, one naive way of doing that is, again, what we can do is sum up all these distances, like between the line and the data point, and try to minimize it. So, let me just give some terminology. If we write this as, let me just write it one more time here, and then I'm gonna define things. So this is the same as yi minus, let's write it as beta naught minus beta 1 xi squared. Okay, so we're gonna define something called the residual sum of squares. Okay, so in other words, what we're gonna do is we're gonna sum up the errors that we're incurring by approximating the price by this line. I mean, by approximating the price from the size by this line, and we're gonna sum up the errors that are happening in the in this plot, right? However, instead of us summing up the errors between, instead of us summing up the errors without squaring them, we're gonna square them. And the reason is, when we work, like, first of all, we don't wanna, the error can be negative, can be positive, so it might cancel each other's. They might cancel each other, so we don't wanna work with positive and negative quantities, and we don't want to take absolute value, because it's not really a good thing to take an absolute value, because the absolute value, as you know, is not a smooth function to work with. So the square function is a nicer function to work with, and hence we square every error that is happening between the sample, the observed data, and the predicted values, right? So if we call y hat the predicted label, and we call this the label, so this is the label. So for each point in this data set, for each I, we have a label, and we're trying to predict it by yi hat. And what we're gonna do is we're gonna try to make the labels as correct as possible, and we're gonna do that by minimizing the distance between the prediction and the actual label that we're looking for. Okay, so this is what we call the RSS sum of squares. So from here, let me just remind you, what's the goal? The goal is to minimize RSS. And why are we doing this? We want to minimize RSS to find beta naught and beta 1. So again, we don't want to choose any line, and the line is defined by beta naught and beta 1. And we want to choose beta naught and beta 1 so that the line minimizes the distance, or in other words, it minimizes the error that is happening. And the way we're gonna do this is by looking at the total error, which we're gonna call the RSS, and we're gonna try to minimize this total error. And once we minimize the total error, for every choice of beta naught and beta 1, we have an error, right? So if I choose the line defined by some beta naught and beta 1, I get some line like this, and I have a corresponding like total error. If I choose this line, I have a corresponding total error. If I choose this line, I have a corresponding total error. And we want to choose the line corresponding to the best beta naught and beta 1. Okay? So let's see how we can do that. So to do that, what we're gonna do is the following. We're gonna appeal to something that we did in the last video, which is the convexity notion, and how we can find global minimum in general. So as you recall from the previous video, we mentioned that when we in calculus, like in Calc 1, when we wanted to find like the minimum of some function, what we did is that we took the derivative and we equal to 0, and we got some critical points, and then we used the first derivative or the second derivative test to identify which of these critical points are actually minima, right? So we mentioned that if we have a function that is convex, right? If we have a function that is convex, minimizing it is so easy because the critical point is gonna be automatically a global minimum. So this is the material of the previous video. So and let me just restate something here. We have this function, which is it's a function of beta naught and beta 1, right? For every different beta naught and beta 1, I get a different total error, right? This is what we are talking about. And we're trying to minimize this function with respect to beta naught and beta 1. We're trying to choose the best ones of these. So since this function is convex, right? A partial reason for this can be if you open this up, it's gonna be a quadratic, like it's gonna be a quadratic function, and a quadratic function, as you know from, for example, x squared, it's convex, right? So you can actually prove that it's convex by looking at the second derivative, but this RSS is actually convex, and thus minimizing it is in order to find the beta naught and beta 1, minimizing it, it's enough to get the derivative of it and set it equal to 0. So it's enough to get the gradient of this RSS function and set it equal to 0, and bam, you get the best beta naught and beta 1. And this is what we're gonna do now. Okay, so to do this, here's what we can do. We first need, okay, so let me just say, since RSS is a convex function of beta naught beta 1, it's enough to use the gradient zeroing method. So it's enough to use the gradient zeroing method to get the best beta naught and beta 1. So in other words, we need to get the gradient of RSS, which is gonna be del RSS by del beta naught, and del RSS by del beta 1, and we need to set this equal to 0, 0. Okay, and once we do that, we're gonna get the best beta naught and beta 1. So this is basically chain rule. I won't spend so much time on this because it's literally chain rule. So what I'm gonna do is I'm gonna just work out the first one quickly, and then I'm gonna tell you what the result will be. So if we take del RSS with respect to beta naught. Using chain rule, you can see that this, so this is the RSS, right? So we're differentiating with respect to this variable. And it's not so hard to see that by chain rule that this is going to be -2, the sum from I equals 1 to n of yi minus beta naught minus beta 1 times xi. Okay. And you set this equal to 0, so this is the first piece here. And then you do the same for the second. So del RSS by del beta 1 equals to 0. And what you get is the following. Once you set these equal to 0 and rearrange and solve for beta naught and beta 1, what you get is the following. Let me just give a few quick definitions here. If we define x bar to be 1 over n, the sum of the xi's, we have this data and it has some xi's. We're gonna take the average of these, the mean of these, and then we're gonna call it x bar. We're gonna call y bar so let me just call some definitions. So these are some definitions from statistics. We're gonna use the y bar also to denote the sum from I equals 1 to n of yi. We're gonna also use sxx to denote the covariance matrix. So let me just use the try it away. So it's gonna be the sum from I equals 1 to n of xi minus x bar squared. So these are just definitions from statistics that I'm reminding you of. And if we write xy, also this is something that we need. This is 1 over n, the sum from I equals 1 to n of, yeah, we can write it this way. xi minus x bar times yi minus y bar. So these are all definitions from statistics that should be familiar to you. And I'm writing these just so that we don't write sums and stuff in the last final answer for beta naught and beta 1. If we set these gradient, if we set these derivatives equal to 0 and we solve for beta naught and beta 1, what we get, turned out that we get that beta 1 is just the covariance of xy over the variance of x, and beta naught is going to be just y bar minus beta 1 x bar. Okay, so this is the closed form solution for linear regression. So let's recap. Let's wrap up here and recap what we did real quick. So in this video, we introduced linear regression, and linear regression, it's the process of estimating the relationship between an input x and a variable and an output y. And we want to do this by a line. We want to estimate this relationship between them by a line. And when we say we want to estimate the relationship by a line, the line has some parameters that we need to know that are not available right away. So how are we going to estimate this relationship? Well, we're going to collect some data set of samples. We're going to, for example, go to different locations and collect the size and prices of houses, for example. And then we're going to collect this data set. We're going to take n samples and collect them all. And then we come to the question of how to find the best line. Well, to find the best line, we're going to minimize the total error that is happening between the prediction and the actual price. Okay, So between the predicted price and the actual price. The predicted price is given by the line, and the actual price is available for us. And we're gonna minimize what's so-called an RSS. So we wanna minimize the RSS function, and we introduced in this video a tool for doing that, and it's called the gradient zeroing method. So whenever you have a convex function, to find its global min, you get the gradient and you set it equal to 0. So over here, getting the gradient is just an easy peasy thing using chain rule. You can get it using chain rule, set it equal to 0, and you get the beta naught and the beta 1 in terms of these definitions from statistics. It simplifies the work. So before we wrap up this video, let me just mention one more note here. Now that we have beta naught and beta 1, the best, let me call them the best. Now that we have the best beta naught and beta 1, we for every input x, we can determine a prediction, let's say for the price of the house corresponding to size x, by taking let me just call it by y hat equals to beta naught plus beta 1 x. So this is what we were looking for. So I'm gonna wrap up this video here, and then we talk about polynomial regression in the next video.